is my pleasure today. We're doing this in English?
Yes.
It is my pleasure today to introduce Danielle Gonzalez-Duque, who is a new postdoc in my research group in the US. And Danielle has done his bachelor's, let me see if I can do this, his bachelor's at Universidad EIA in Medellin in environmental engineering, his master's at Universidad Nacional de Colombia in water resources, and his PhD in Vanderbilt University in environmental engineering, and has recently published I think the last of his PhD chapters in water resources research multiple times. And another cool thing about Danielle is that he is the recipient of the AGU Horton Graduate Student Hydrology Grant, which is awarded to only 2 hydrology students every year, and it's very competitive. The funding rates, I think, are typically lower than like the ERC. So it's my pleasure today to welcome Danielle and to present his mostly his PhD research, but a little bit on where he's going in our group now for his postdoc.
Thank you. Thanks a lot, Autor, for that introduction. So besides that, I wanted to also sort of acknowledge our funding sources for all of this research that I have been doing, and our collaborators during my PhD, and also our new collaborators as well during my postdoc. Before I begin, I want to say happy 4th of July. I couldn't bring fireworks here, but this is as close as I can get. So happy 4th. Okay, so as an outline for my presentation, I want to divide my presentation into 2 parts. First part, I will be talking about my current research experience, what I'm going to do for my postdoc. And on my second part, I'm going to talk about more of my PhD research. So to start with my current research, I'm interested in looking into saltwater intrusion models. And in this case, you know that saltwater intrusion is really important for groundwater management. We don't want to be tapping into these saline ecosystems. But what we are interested in looking at is sea level rise. What is the effect of sea level rise in saltwater intrusion problems? And we can have a lot of problems with this sea level rise. First, we have groundwater hazards, where you have groundwater salinization going in. And because of that, you have groundwater shielding and also groundwater flooding in some of these areas. And that has implications for environmental and health hazards, where you can start to have volcanisation and contaminants that were trapped in the soil in the unsaturated zone. And these can reach wells that are used for public use, and also this can affect ecosystems as well. And you can also have infrastructure damage, where you have impacts on the drainage infrastructure, but also corrosion and uplift of building foundations, among other problems. So if we were to model some of these systems, this is, let's say, our conceptual model, and in this case, we want to make our life a little bit easier, but only calculate this x of the flow, this distance between the coastline and where you have the transition, that saltwater intrusion. So if we want to model this, we can do different things. We can first have a model selection. Are we going to do this in 1D, 2D, 3D? Are we going to do it homogeneous or heterogeneous or anisotropic? And from there, depending on the selection that we make, we also have parameters. What is my hydraulic conductivity? What is my porosity? We're going to use dispersivities. What are the dispersivity values for this as well? And of course, we also need data because we need to calibrate our models and also validate them. So we need the aquifer thickness, also the recharge in current conditions, and the sea level. And this problem, well, and another condition that we also have to take into account is if we're going to model in sea level rise conditions. In this case, we want to measure this delta of XT. And in this case, we will also need the sea level rise information and also projected values for recharge. So, depending on the model that we pick and the decision that we make, we can think that, depending on the complexity, we might have a better accuracy in our model. What I mean by that is, if we start including more complexity in our system, you start getting models that are more accurate. We expect to get models that are more accurate. Let me show you some of the examples that we have for modeling these approaches. So from really classical models, like the ones that we do in 2D, where we have the Guyton-Herzberg relationship, where it's just the definition of the saltwater intrusion curve is defined by the difference in densities. And this work is related as well for fundamental work done by Custodio previously, where you can calculate exactly where this intrusion is at the bottom of the aquifer. So these are analytical solutions, and these analytical solutions are easy to use if you have information, of course. And you can use this information to essentially calculate this at a global scale. And this is a work that has been done by our collaborators and is now being in the process of being published. This is work from the Jet Propulsion Laboratory. And I missed to mention this project is funded by the Department of Defense. And the Department of Defense is interested in knowing what is the problem of saltwater intrusion in some of their sites. We are using also all of this information to be able to characterize this at a global scale. Now, with this information, of course, this is an analytical solution, we have a certain degree of accuracy in our system. We can also do models that are a little bit more accurate. And in this case, it's a 3D model. I think this was published in Nature. And the area that you see there, I know is difficult to see, is the San Francisco Bay. And in this case, they did a 3D mud flow model where they can use different complexities or include different complexities and look what happened when you have sea level rise of 1 meter, 2 meters, all the way to 5 meters. And that is important for decision making, of course. So if we were to try to compare, depending on the model that you pick, you can compare how good is this prediction versus how good are the other predictions as well. But as you increase the complexity of the model, you are also increasing the uncertainty of it. You are increasing the amount of degrees of freedom that you have in your model, and thus you have to measure them. We'll have a sense of how is the hydrologic conductivity distributed throughout this whole region. Do you have an isotropic behavior or heterogeneous system, and all that. So your uncertainty increases. That doesn't mean that your accuracy decreases. That just means that you are getting some results, but those results are uncertain. Okay? And part of that uncertainty comes from the model selection itself. So what I want to do in the first part of my postdoc is to ask ourselves, how do the decision of the model selection affect the uncertainty of the process we're trying to represent, in this case, of water intrusion? And for that, we can do different things. We can pick really complex models and try to compare it with analytical solutions in a way to achieve this uncertainty. But that will always only tell us how good is the analytical solution for one system in one specific region. So what we decided to do, at least for this moment, is to do some intermodal comparison using synthetic scenarios. And in this case, we're going to use synthetic landscapes, synthetic landscape creation, a package that is called FastScape. And this FastScape approach is allowing us to get different landscapes that we will be able to use. In this case, if you pick one of these, to be able to delineate the different catchments in the areas. And from these catchments, we can do simulations on some of these catchments that are releasing water directly to the ocean. So as an example here, these are some of the preliminary simulations that we have for really simplified systems where we are able to reproduce using mud flow, some of these interface, and with that calculate the saltwater tone in these areas, and we can compare these with actual with the analytical solution as well. The good thing about using this synthetic approach is that we can essentially make these problems as complex as we want. And in this way, we want to have a sense of, in doing a global sensitivity analysis, have a sense of what is the model selection uncertainty versus the parameter uncertainty and also the data uncertainty and restrictions. Again, this is just a work that I just started to do in this first month of my postdoc, and this is the direction that I want to take, at least in the first publication. Now, this is for my postdoc. Now, let me go to the meat of my presentation and go to work or to see what I worked for during my PhD. And in this case, I was interested in looking into two distinct systems. That's why I said from mountains to bedforms. And in these two systems, I was interested in looking at the multiscale groundwater dynamics and its influence on solute and energy fate and transfer. In this figure that you see here, this is Valles Caldera in New Mexico. You can see these mountains there at the back. And you can think how water moves through that mountain system and recharges the alluvial aquifers that you have in this area. If we do a cross-section of this mountain system, it will resemble something that looks like this, where you have the mountain on the right, the basin field on the left, and they are connected through faults. If we think about how water moves through that system and reaches that basin field, you have rivers, of course, that flow through the surface, but you also have water that is flowing from the first topographic relief systems all the way to the basin field. Now, in the mountain block, you have a more Tolkien approach of flow, where you have local flow paths that recharge these local flow systems, where you have rivers, and you can also have regional flow paths. These regional flow paths are moving through fractured bedrock. And these are important because in this case, we wanted to have an approach of how to characterize this regional groundwater flow. How deep is the regional groundwater flow? In a way to be able to answer questions like how deep is the critical zone? How deep water is actively circulating through that mountain system? So that is the first section of my PhD. In the second section, I was interested in looking at more localized systems. And in this case, I was interested in looking at how rivers connect to the groundwater system. You know that rivers are not pipes. They are more like leaky pipes. They are constantly exchanging water with the groundwater system. And in this case, I was interested in looking at hyporheic exchange processes. For those of you that don't know what a hyporheic exchange process is, it's essentially water that leaves the river to enter into the groundwater system. And in this groundwater system, you have a lot of biogeochemical reactions occurring. And from there, the water gets back into the river. And you have water with different chemistry going. And that is what I was interested in looking. I will talk about that more. And in this case, I was interested in looking at what is the role of river corridor connectivity on these ecosystem services. Okay. Now, let me try to entice you as to why deep groundwater systems are important. First, some definitions. We have the mountain block on the right, then the mountain front and basin floor on the left, and again, they are connected to a fault. When we simulate these systems, what we usually tend to do is assume that the depth of circulation is less than 100 meters. What we usually do is say, well, what is my depth to bedrock? And from there, I place a no-flow boundary, and there is no flow going after that. However, in some of these systems, you have fractured bedrock. And if you do that, you are effectively neglecting part of this regional groundwater flow that is occurring through that area. And that accounts for the budget of water, energy, and solutes that eventually reaches the basin. And we have seen this with data. This is a work done by Jennifer McIntosh and Grant Ferguson, where they look at meteoric water in wells all around Africa. And as you can see, they were able to detect water circulating kilometers deep, in some cases 2 to 5 kilometers deep. And this happens when you have high topographic relief systems. And that makes sense, because you have a lot more potential energy to drive this water all the way to 5 kilometers in some cases. But then, why is this important? Why do we care about these systems? If we were to do a simulation of the solute concentration around this area, it will look something like this, where you have in here discretized, fresh, brackish, and saline water. What happens is that as the water gets trapped into the regional groundwater system, it starts to dissolve minerals. And in that dissolution of minerals, you start increasing the total dissolved solute content, and your water becomes brackish and then saline. So what we usually do in arid and semi-arid environments is to tap into these freshwater resources for municipalities and public use. And we are actually depleting these resources faster to what they can replenish. And that is something that is happening in arid and semi-arid regions. So if we look at the water supply sustainability risk index by the year 2050, you see that in the United States, the majority of the central states and southwestern states, you have a high to extreme risk of not having a sustainable water supply by the year 2050. And this is important. And this happens because of population growth, of course, that drives demand, but also climate change that is exacerbating this issue. So what people have been doing in some of these states, most of these states, is to tap into brackish groundwater resources. What they do is go down to these other resources and extract that water. They use the salinization plants to be able to use it, and then, essentially use it for municipalities. But then we run into the same issue that if we are also using this aquifer, and this aquifer comes from the regional sources, that will take a long time to replenish. So we sort of fall into the same wall. So the idea behind this is that regional groundwater flow is important because it is also being accounted for that regional system. Okay? So how do we map this? And this is related to the work that you're also doing here. In a way, it's using geophysics. In this case, we're using geophysics as a proxy to detect these deep groundwater systems. But we can do several things. We can use active methods like electrical resistivity topography, where you place some sensors on the ground and you start sending currents between them and measuring in order to. Okay? But you can also have passive methods. And these passive methods, one of them is called magnitude calorics. For those of you that know, imagine that it's just a station that is able to capture fluctuations in the magnetic field of the Earth. So all the waves that travel down the Earth from these variations hit the ground, some of them come back, and some of them are able to penetrate deeper into the soil, and these instruments are able to capture that variation. And the longer you leave the instrument, the deeper you get. In some of these cases, you can get even 5 kilometers deep, or 10 or 20 kilometers deep for some of these systems. And that is where the regional groundwater flows are flowing as well. So let me show you some measurements that have been done in the field by other authors. One is the Yangtze River in China, where you can see this is the profile that you have in that area. So you have recharge from these two mountain sources, and this is the profile where they did magnetotelluric measurements. And in these magnetotelluric measurements, you see differences in the resistivity patterns. And in these differences of resistivity patterns, you can sort of see some of the circulation cells going through that system. And as you move down, you start to see regional sources as well. What we can argue is that what we are seeing there is fresh water going in or recharging that system. And as you move down to the regional groundwater system, you start to see brackish and saline water. Let me show you some other examples. And this is the Tula Rosa Basin in New Mexico. This is the place where I based most of my studies. It is important to mention that this was a paleo lake thousands of years ago, and it got evaporated over time. So you have a lot of gypsum deposits close to the surface all around this basin, but also you have outcrops in the Sacramento mountain system. What they have shown is a similar conceptual model that what I have just shown you, where you have a Sacramento mountain system recharging fresh water, and as that water gets trapped into a regional water system, you start to dissolve minerals, and then your water becomes brackish and then solid. And they were able to see this with data as well. They made an ERT measurement close to White Sands National Monument, and in this place, the authors argue that what you are seeing there is fresh to brackish water sitting on the sand dunes that are sitting on top of clays filled with saline water. So from this analysis, you can sort of say that your geophysical observation is affected by multiple things. And two of the things that are importantly affected for is first the subsurface architecture, what type of ecology we have in that site. But also it's being affected by the fluid chemistry. So is your water saline, is your water fresh? So what we wanted to see here is how much information about the nested nature of the flow field is captured in such observations. And for that, we created a theoretical approach. With that, we created this virtual reality where we have in this system the mountain block on the right, the alluvium on the left, and the fault connecting the mountain block and the alluvium. We did several simulations with different systems where we vary the topography, essentially the regional topography, we make it higher or lower, and also the local relief system as well. We accounted for some heterogeneity using equations that we found in the literature where you have decay and permeability with depth. And in this case, we also accounted for an anisotropic behavior in the first kilometer, and after that, the permeability decays potentially with depth. And we relate that to also porosity, and our porosity is also decaying exponentially in the potential. Now, for this system, we did a groundwater flow and transport of heat and solutes model for all the system. I've shown you here the equations. If you want to ask about them, we can talk about more about them later. But I want you to understand the concept. What I did here was to create, again, groundwater flow and the transport of solutes and heat through that system. And we coupled all of the system using equations of state. So we're essentially varying density and viscosity throughout our simulations. And from there, we also incorporated a dissolution rate, it's a first order dissolution rate that accounts for that dissolution of minerals and increasing concentration. And the dissolution rate is also linked with temperature through an Arrhenius expression. Okay? So let me show you some of the results. And this is for the results of one of the systems where you can see here clearly in the streamlines where your local and regional flow paths are located. And from there, the colors are the Darcy's velocities for that region. So as you can see here, you have the local flow paths, and in these local flow paths, you have also convergence of regional flow paths. And that convergence of regional flow paths creates some areas with lower velocities. And these areas with lower velocities are called stagnation points, stagnation areas, the different names for this. So what it essentially means is that water becomes almost stagnant in these points. So that is where you expect to have the most accumulation of solids. Okay? This is one of the simulations again. We also did that for higher permeability systems where you also see those stagnation areas located around that area in the median branches of local and regional flow paths. And we did that for different models. For different regional topography. So as you can see, if you have no regional topography, you have a deeper penetration of the local flow paths, and that's what we start to see. Now, this has implications, of course, in the water ages. In the water ages, I'm discretizing here by colors, water that is less than 10 years, from 10 to 10 years, to 100 years, all the way to 10,000 years or more. Okay? So in the mountain block, you have mostly fresh water that is really young going in, and as you move towards the alluvium, you have a little bit or fresh water and also young water going in, and then as you move further away from that, from our mountain system, you start to see the emergence of older and older water. And this has implications, of course, for concentration. So in this case, I did also concentrations using the same discretization that I used before, where you have fresh, brackish, and saline water. And you can see here in these points, where you have the stagnation areas, you start to have the accumulation of solids happening through that system. Okay? And this is recurring through most of our simulations, where you see that in the systems, you have also the stagnation areas located here. But as soon as you remove that local relief system, you have mostly regional water flow going through the system, so those stagnation areas disappear. Okay. Now, let me show you some analysis. This is a theoretical approach. We didn't do it exactly inferred. We didn't validate it in these models with any real data. We were doing that at the end of my PhD. I'm still working on that. But just qualitatively, what I'm showing you here is carbon-14 measurements done in the Rosa Basin. Let's just assume that our model here resembles this cross-section that you see there. What I want you to see here is that water that is close to or in the Sacramento mountain systems is relatively young. And as you move further away from that mountain block, you start to see water that becomes 10,000 years older or more. Okay? In terms of water quality, this is what is happening there, where you see water that is close to the mountain block or in the mountain block that is fresh. And as you start moving away from that system, you start to see brackish and then some spots of saline water just popping up. And that happens because of these gypsum deposits. We have a lot of gypsum deposits located around the whole basin, but also outcrops in the Sacramento mountain system. So what about imaging these systems? How do we do that? There are different petrophysical relationships to do that, and the one that is most commonly used is Archie's law. Now, we wanted to use an extension of Archie's law, that is the Glover's model for bulk resistivity. What is different in this case is that you are accounting for the resistivity or the conductivity in this case of the fluid times the porosity, but you are also accounting for the variations in the porous media resistivity as well. Okay? What that means is that if you have a system that has high porosity and is saturated with water, most likely the resistivity that you are seeing there comes from the fluid. However, if you have a system that has low porosity and is really packed together, most likely the resistivity that you're seeing there comes from the porous media resistivity. And as we have information from concentrations and temperature, we were able, and assume some idealized porous media resistivity, we were able to characterize or calculate what is the resistivity in our system. And this is in millimeters, where you see the difference between fresh, brackish, and saline water delineated with the contours. And as you can see here in the alluvium, you see a clear difference between fresh, brackish, and saline water. However, in the mountain blocks, something interesting happens. What you see at the top is mostly fresh water flowing into that system. But as you move down and your water becomes brackish and saline, you start to see these pockets of low resistivity. And these pockets of low resistivity happens in the stagnation areas. Okay? Now, as soon as you keep moving down, your porosity decreases. And as your porosity decreases, your resistivity goes to the porous medium resistivity, and that's why you cannot see any contrast back there, down there. Okay? So we did the simulations, and part of what we wanted to do in the future is to, if we were to go in the field and try to map the systems, would we be able to measure these things, even though they are really small, at least in our simulations? So what we decided to do was to use forward and inverse models for that. And in this case, each of these inverted triangles that you see here, let's say that is magnitude caloric station, okay? And this is our forward model. So in this forward model, what we do is essentially capture what is the resistivity happening below this station, okay? And we take that information, put it into a software that allows us to do inverse modeling of magnitude telluric data, and this is the results that we got. So as you can see, they are not exactly the same as we expect because of the inversion, but you can see that those pockets of low resistivity still in our simulations. And that is something that is encouraging to us to look into the future if we go to the field and go to the Rosa Basin to see if we're able to know those. So solutions for these sections, is groundwater solute patterns are strongly dependent on topography, yes, geology and dissolution rates. And also we see that resistivity patterns follow areas with high solute concentrations, as we expect. It is interesting to us that magnetotelluric surveys are able to capture these stagnation areas, and that could serve as a proxy to detect the depth of hydrocirculation, because remember that these are happening in stagnation areas where you have the regional groundwater flow circulating. We also think that more rigorous inversion techniques could isolate this nesting effect, and that is for future work as well. So again, this is one of the parts of my dissertation. Now let me switch to something a little bit different. And let's talk about rivers. This is the Clinch River in Tennessee, and here I was interested in looking at the multi-scale nested nature of river connectivity. If we think about the connectivity that happens through that system, we can think of hyperrate exchange processes, as I already mentioned. And what process here happens longitudinal, where you have flow going through the bedform, and that is what Autor studies in her work. But what I was interested in looking in these systems is also, if you have a meander going from this side to the other, you have the water table of the meander here, and once you go to the other side of the bend, you have a difference in heads. And that difference in heads is what is driving flow through the meander system. And that is what we call sinuosity-driven hyperrheic exchange. That is just lateral exchange that occurs through that system. And this is important because it works as a biogeochemical reactor. And it gives a lot of ecosystem services, such as contaminant buffering, thermal regulation, and also metabolism and nutrient cycling. Okay? So we decided to focus on these areas and study them a little bit more. Our intention, we wanted to get out of this, and we are still working towards that end, is to first gain mechanistic understanding of how this process occurs, and from there characterize meanders at a continental scale. And we are working towards that. So let me show you the gaining of that mechanistic understanding. As I mentioned, rivers are not pipes, they are more like leaky pipes. They're constantly exchanging water with the groundwater system. This is a meander, the Yakima River in Washington State. And from here, you can see that from one side of the meander water bend to the other bend, you can have hyperrheic exchange processes occur. Okay? So that hyperrheic exchange process is driven by the topology and geometry of that meander. But it's also being regulated by the amount of regional groundwater flow that is pushing into that hyperrheic exchange process. So what I mean by that is that if you increase your regional groundwater flow, you're effectively compressing that hyperrheic exchange zone. Okay? And we wanted to see that. We wanted to ask ourselves, what is the effect of the meander topology, that is our driver, and the regional groundwater flow, that is our modulator, in the hyperrheic zones, hydrodynamics, and biogeochemical. Okay. So let me show you our virtual reality. As we know, meanders are, some of them tend to be periodic, some of them tend to not be periodic. But let's just assume in our case that they are periodic. And in this case, we're picking just one bend of the meander where we have our hyperrheic exchange process. We also know that meanders have all shapes and forms. But we wanted to make our life a little bit simpler, so we use some mathematical expressions that allows us to see typical meander form, meander shapes. And these equations have been used by the morphodynamics community in a long time. Okay. And this is our model. In this case, we have the river at the top and the alluvial valley at the bottom. It's like we are looking from the bottom. Okay. We did groundwater flow and transport modeling for this. These are the equations. Again, I want you to understand the concepts of it. Just skip them and just to show them and skip them for now. But if you're interested, I can go over. Okay. So we did a dimensional analysis of the groundwater flow equations. And with that, we came out with 3 dimensional quantities for flow that allows us to explain the process. In this case, the first dimensional quantity is the sinuosity. And the sinuosity is just the distance of along the channel divided by the distance, the horizontal distance. Okay? If this number increases, the sinuosity increases, it means that the neck of your meander becomes narrower. Okay? The other dimensional quantity that I want you to see here is the ratio between the slope that you have through the alluvial valley and the slope that you have through the channel. If this number is positive, it means that your river is gaining water from the groundwater system. If this number is negative, it means that your river is losing water to the regional water system. If it's 0, it means that we only have direction, flow going in the direction. Okay? The last dimensional quantity just appeared out of our analysis. We're not interested in changing this because in this case we're interested in the modulator, in the driver that is the sinuosity, and the modulator that is this pi j. Okay? So we log the values here and we compare these two. Now let me show you some of the results that we got out of the dimensionless integrated flows. In this case, these are the different meanders. I missed to mention we are doing integrated flux vertically, so we are only doing simulations in 2D. And in this model, what you can see here in color is the dimensionless narcissus velocities, and the different streamlines show the extent of the hyporheic exchange. Okay? And these are neutral conditions. Flow is only going in this direction. So as you can see, for different meanders, you have an extension of your hyporheic exchange zone as we expected. That is where water is flowing. And from there, we calculated this integrated flux going through the hyporheic zone and only through the hyporheic zone. Okay? And that is the figure that I'm showing down here, where you have the log of that integrated flux flowing. And in the x-axis, you have sinuosity. What that means is that each of these meanders is essentially these points in this graph. So as you can see, for neutral conditions, we increase our integrated flux a little bit. But what happens when you have gaining and losing conditions? Well, from gaining and losing conditions, you see that for strong gaining conditions, you're effectively compressing that hyporheic exchange zone by few orders of magnitude. Well, by a lot, and that changes your integrated flux by a few orders of magnitude. However, as you start having a meander with a neck, the gradients that happen that occur across near the neck are higher than the ones that are going through the regional groundwater flow, and that is counteracting the effect that you have in the compression. So as you narrow your neck of the meander, you expand the hyporheic exchange zone. And that is important to us because it means that meanders that have a narrow neck have more exchange than the ones that have a wider neck when you have regional groundwater flow influencing the process. Okay? So let's talk about biogeochemical reactions. And in this case, well, again, this is our meander or hyporheic zone, and we studied gaining and losing conditions. And we were interested in looking into nitrogen cycling. So in our model, we model respiration, nitrification, denitrification, and also microbial uptake of ammonia. And as you can see, you have DOC all over the place, well, in all of the equations that are really important. So we also have a term that accounts for dissolution of DOC in the system. We were interested in looking at nitrates, and essentially, what is the mass of nitrates going in and the net mass of nitrates going out? And then we devised this P metric that we call the potential of denitrification. This potential of denitrification is the mass of nitrates going in minus the ones going out divided by the ones going in. What that means is that if this potential of denitrification is larger than 0, it means that you are acidic. You are retaining, you are denitrifying the system. If this number is less than 0, it means that you are a source. You are actually producing those nitrates. Okay? And with that, we calculated this matrix. And this matrix has a lot of information. Bear with me. In colors, what you're seeing here is this potential of denitrification, where the blues are sinks and the reds are sources. Okay? And we also did a dimensional analysis of the transport and reaction conditions. And we came out with 14 dimensionless quantities, I think it was. But out of all of those dimensionless quantities, 2 of them are the ones that are driving most of the reactions. One is this ICOC, that is the ratio between dissolved organic carbon and dissolved oxygen, and the other one is the Lamport number for oxygen. So let me just explain first these ICOC. So when you have an oxygen-limited system, it means that you have more carbon than oxygen. Then your oxygen is used for respiration, for mostly, but part of it is also for nitrification. But then your system starts to become anoxic, and from there you see mostly denitrification. That's why it's happening here. Now, in carbon-limited systems, you have a surplus of oxygen, and that surplus of oxygen, well, the carbon that is there starts to be used for respiration, but it gets to the point that you have a lot of oxygen there still remaining, and that is why you start to have nitrification in these areas. From here above, I will explain you in just a moment when I explain the Dampoler number. So let's talk about the Dampoler number. And in the Dampoler number is a ratio between how fast reactions are occurring versus how fast the fluid is being adapted through that system. I'm going to use an analogy to try to explain this system a little bit better. So imagine that you have a treadmill, and in that treadmill you have just cookies just passing by. And you have a cookie monster that is just eating the cookies as they move, okay? So for reaction-limited system, that means that that treadmill is just moving too fast. So the cookie monster is really stressed out and is not able to eat all the cookies, okay? So most of what you see here is white. That white means that you have almost conservative transport. There is no reaction, okay? Now, for transport-limited systems, that treadmill will start moving slower and slower. And the cookie monster is happily eating those cookies. Sometimes it eats chocolate chip cookies, but once they run out, they start to eat oatmeal cookies and all that. So then the cookie monster is happy in this case, okay? So what happens here is that, yes, in the reactions that I showed you here, you have a carbon-limited system, you have more oxygen, then you're producing nitrates. But it gets to the point where the dissolution of particularly on the carbon kicks in, and that dissolution, it counteracts the effect of the carbon-limited, and then you have a system that has a surplus of dissolved organic carbon, and that's why in this part we have a single. Okay? Now, we have information for different rivers around the world with this information, and as you can see, this is where your typical rivers fall into place. Okay, so you have the 5%, 95%, and the 25 and 75, and the median of both of these distributions. And we're okay. Most of the meanders are actually here in this area. That's what we expect. And each of these pixels is one simulation that we did for these systems, where you have the mass of nitrates going in and the mass of nitrates going out. Now, let me show you the results for the different systems that we explored. In these systems, we assume that the water in the river was polluted. So it has a nitrate concentration of 8 milligrams per liter and ammonia of 5 milligrams per liter. That's why we start to see these concentrations. In the paper that we recently published, we also accounted for this and did simulations for pristine conditions. You can see them there in the paper if you're interested. So what you can see here is, as I already mentioned, nitrification in carbon-limited systems. Here. But you also see denitrification in oxygen-limited systems, the one that you have here. And something that is interesting to see is that denitrification potential decreases with increases in velocity. As you can see, this red area starts to move up and up and up. And what happens is that as you narrow the neck of the meander, you have a fluid going through that neck of the meander, and that is moving faster. So your meander is not as good as at removing nitrates as meanders that have a wider neck are. Okay? We also did the simulations for gaining and neutral conditions, and we didn't see a lot of changes between them. The only change, or some change that we see is in this case, and in this case is because this hyporheic exchange zone was so little that it was capturing part of what was happening in the regional groundwater flow. So don't pay a lot of attention to these results specifically. But as you can see, they are really similar to other systems. What is different is the amount of exchange that is occurring. So in these systems, you see a few or 1 order of magnitude difference between these two. Okay? So you don't have a lot of water that is actually being processed. Now, what about POC? What about particular organic carbon? As I mentioned before, in this area, this is the potential of is the solution of carbon in this case. And as you can see, in all this area, when your dissolution of carbon kicks in, is where you have production of carbon in that area. And that is what is counteracting that effect of the nitrification. Okay? Now, what happens if you increase the amount of particular organic carbon in your system? Well, in this case, this area increases, and you're. What happens if we remove all the particular organic carbon from there? So in this case, essentially, you don't have any production of this organic carbon, or dissolution of this organic carbon. And in this case, you start to have nitrification throughout the whole area. And that is important for what we see. But particularly, what I want to make here is that particular organic is important for the simulations that we are doing, and we should also measure the systems a little bit more. The problem is how to do it. That comes into another discussion. Okay. So finally, just some conclusions. Regional groundwater flow, water lakes and hyperlake zone, and it seems that low sinuosity channels are particularly sensitive to that. We see that the nitrification potential decreases with increasing sinuosity, and that is important for river restoration strategies as well. And we see that the ratio of dissolved organic carbon and dissolved oxygen in the channel, the Autor number for oxygen, and the substrate availability plays a crucial role in this biogeochemical potential. I wanted to make a note as well, and is that heterogeneity is important in the systems. We assumed that these systems were homogeneous, which we didn't account for that. But depending on where you have your particular organic carbon in the meander, that will change the amount of the net effect of denitrification in your system. And before I finish, I just wanted to acknowledge Audrey, of course, for everything, for all the amazing work that I've had with you. And I also want to acknowledge my former advisor, Jesus Gonzalez, who's now working at the National Lab, a few collaborators at New Mexico Tech, Mark and Sherry, and of course, UBC for hosting me during these 2 months. If you're interested in looking at these 2 publications, feel free to scan that code that is linked to my social media, so you can essentially. And I'm happy to answer any questions.
Daniel, do you want to moderate your own questions, or do you want your questions?
It's a nice representation. I'm so excited about the biochemical reactions that you were explaining with the use of the organic carbon. I don't know if I understand, but I think that the sinuosity is similar maybe in some physical way, maybe mixing some, I think so, when we are crossing this. When you say that this have a relationship with the nitrification, can you show me that for a second?
Which slide?
I think here, that you say that the nitrification decrease will increase in sinuosity, so this is, I think that's like a physical barrier or something like this.
So yes, so what is happening is that in this case, the flow that is moving closer to the neck of the meander is moving too fast for reactions to occur.
Excellent.
So your meander is less effective at denitrifying that system.
Yeah.
And what we are seeing here is the net denitrification potential. So what is the mass of nitrates that we are pushing through that hyperradius zone versus how much is the nitrates that is actually leaving that hyperradius zone?
I feel like I've asked you this before, so forgive me if I did and I've forgotten, but your sort of efficiency of nitrification or denitrification is with respect to water that enters the hyperradius zone,
Yes.
not with respect to the downstream flow of river water. And I fully understand that rivers have a continuum of all degrees of sinuosity along them. But let's say you had a river with only high sinuosity or only low sinuosity, that affects the frictional resistance and the way water moves downstream. Did you think at all about efficiency with respect to river water flow, like the flow of nitrate in surface water?
Yeah, that is a really good question. Yes, no, we didn't account for this in our simulations, and we have seen different works by different river stages, for instance, create different residence times in your system, and that is something that has to also be accounted for this problems. In this case, we went little simple, maybe too simple for our understanding. But yes, that is important. Also, reactions that happen in the river are important. We know that the concentration of oxygen is not the same throughout the whole system, and the ocean as well. So yeah, we didn't account for that.
Because what you plot here, the colors, it is the how much gain or electrification that you have versus how much flow there is.
It's
how much nitrogen comes into the ground.
Yes. In this case, what we did was assume that the whole river has the same concentration of 8 milligrams per liter and of nitrates and 5 of ammonia, and that the integrated amount that is going in the mass that's going in versus the one that is leaving the system.
I think that someone is maybe some questions online because I can analyze here.
Just explain.
Albert is there, I think.
If you have any questions.
No, you have to leave
Buenas.
Albert, do you want?
Yes, can you hear me?
Yes.
Yes.
I have one question. First, congratulations for the presentation. It's really nice and great. And I have a couple of questions of the first half. One, maybe I missed something, but I'm not clear about how you define these stagnant points with the geophysical data.
Yes,
I
that
don't
is.
know if you can explain a little more on that.
Yes, so the stagnation points, they don't come from the resistivity data. They are the resistivity. Let me just go back to that slide if I can. There you go. So the stagnation points they are not exactly defined by the geophysical data. They just happen to occur where you have where your velocity field shows where your stagnation points are. So they're basically points where you have accumulation of solids, and that is where those accumulation of solids in these areas is where you see these contrasting resistivity patterns. So they don't come exactly from the resistivity; they come from the distribution of solids throughout the whole system. I don't know if that answers your question.
So you obtain that from the model, not from the data.
So
from your simulation.
I mean, you make a simulation.
yeah.
Okay, so I think you make a simulation, and that simulation sort of simulated the real data.
No.
Then you do just to check whether the method works.
Oh yes, no. So in this case, in the inversions, but yes, it's a good question. So for the forward models, we assume well, this is the resistivity patterns that we will find in the field. Let's just say that. And how we place the stations, we wanted to place them in a way that we were able to constrain where we expect to have these stagnation areas. And these happen close to where you have discharge, so close to rivers. And that is how we want to, if we were to go to the field, where we will go and put our empty stations.
Okay, I have a second question. It's about the regional faults that you put it in your geological cross sections. I'm surprised because according to the flows that you are showing us, they don't have really an hydrogeological role. I'm surprised because, or they are impermeable usually, or more impermeable, more permeable than the surrounding geological matrix. But according to your models, look like they don't have much hydrogeological role. It's what did you observe, or how you simulated that, or what hydraulic parameters did you locate in these faults?
Yes, so that is another important question. And again, the simulations that we did are purely theoretical, and we assume decay, permeability, and porosity with depth. Yes, some of these residence water ages are millennia old, and they sure have an impact of the geology that you have in the site. And that's why we're trying to do more realistic approaches of actually using the topography of the site and starting to do more calibration of these systems to be able to account for that differences in geology as well. In this case, they were just idealized systems.
And with the okay, and you could you see something, or do you have, or the geophysics could you give you an idea about the role of these regional faults in your flow system?
That's a good question. I don't know. I think it might, yes, but I'm not sure.
No, because according to your conceptual model, if the fault is less permeable, you should see an increase, or an increase of the saline part in the mountain part. And if
Oh, yes,
they
yes,
is more
yes, yeah.
permeable, you should see like an upward flow from the different systems, depending of the resolution of your profiles. That is the other thing. It's only to know. I mean, I don't know. I haven't seen this data before, and I think it's great. It's only to know if you could detect something or get the feeling of something on that.
Yes, no, that is a good question. So, yeah, in this case, we assume only one permeability for the fault, and that might not be the best case. And you're right. If we reduce the permeability of the fault, we will have a back increasing solid concentration around this area. What is happening in our simulations, actually, and just to mention that, is that part of the flow that you see here is actually flowing downwards through the fault. And it's leaving the system downwards to the fault and then going back up. That's why we see this. But yes, that is something that we also need to explore in these systems.
Okay. Thank you. Good job. Great work.
Actually, while we're on this, I do have one more question. And I guess maybe before I ask it related to what Albert was just saying, I mean, I see how you would set up your survey in a very different geometry if you wanted to see what was happening along the fault, and that you were setting it up more to look for these stagnation points. And so that leads me to my question. Well, and so it's interesting to think about what would happen if you wanted to see the faults zone in more detail, but my question is related to the stagnation points you're looking at. Do I understand correctly that part of the reason you see them so well is because you're in really low porosity media?
No, in this case, well, it's two things.
Like the fact that that whole thing is mostly red except for the stagnation points and not sensitive to the pore fluid conductivity is because we're in low porosity.
Yes, in this case, in this specific case, yes, it's because of that. But what happens is that if we increase also the porosity, what you will start to see here is the difference between fresh and brackish or saline water. And in that case, you can also detect where these points are located.
So, but is there a transition? No, I guess there's no transition zone where it starts to get blurry. You're always good. It sounds.
Yeah, if you have enough control. No, that is another thing that is important to mention here, and is that in these cases, we assume a high dissolution rate for the system because we were trying to reproduce the Tuna Rosa basin where you have these deposits of gypsum. In the cases when you have lower dissolution rates, I don't have the results here, but we also include them in the text, where you have a lot of intrusion of fresh water that goes really deep. And in those systems, it goes so deep that you are not able to characterize where the regional groundwater flow is going. Because most of this will be red, and then it switches to low porosity, so then it keeps being mostly red for most of for the whole system. Now, that said, again, these are idealized simulations. The geology of these systems are way more complex than that. And to talk about measurements in the fault, part of this project and part of the work that we're currently doing with New Mexico Tech, they actually measure or did magnitudinary measurements close to the fault, because what they were trying to see is they have a geothermal system that is traveling through this fault system. And they think that this geothermal system comes from regional sources. And that regional sources is actually also recharging the Rio Grande Rift. So they did some of this grab some of this data. They have not analyzed it yet, but we are expecting to see if we can see some of this behavior occurring there. I don't know if there's more questions online.
I have a question also related a little bit to this salinity and age and stagnation points. Because I don't know whether in these models you assume a sort of relation between salinity and age, for instance. Because I would guess that indeed with higher age or more age, you got more saline, but you reach some sort of maximum.
Yes, that is true. Yes.
I don't know whether your model takes it into account, it's just linear.
No. It is a first order reaction rate, and we set up the threshold to be, I think it's 0.3 kilograms per kilogram, and as soon as you reach that value, you start to precipitate. That is the maximum of some.
Okay, so you reach something.
Yeah, you reach it.
And in these stagnation points, because I guess that diffusion or dispersion of these kind of things will tend to, I don't know, disappear these stagnation points, or I don't know how much.
Yes, that is another thing that is important to mention. So, few things on there. So first, these stagnation points occur where they are because of the topography that we have in our system. If we have a different topography, they will be elusive, more difficult to find, I'll just say that. And in here, we're accounting for steady state conditions. So the locations for where they are is if this system was under steady state. But they can vary depending on the stage of the recharge that you have, and yes, the other
Yes, but thinking of a steady state situation, also with solute transport of energy, I mean, wouldn't these stagnation point disappear, or the salinity be the same as the saline? I don't know.
yes. So what is happening here? Sorry. What is happening here is that the flow that is going to the fresh water is so fast that any, let's say, diffusion that happens from these points out in the system gets removed or flushed out really quickly through the freshwater system, through the local groundwater system. So that's why they are, in a way, stable through this area.
Yeah. But it would also depend on diffusion or dispersion.
Yes, that will also depend on diffusion and dispersion in the system, and it gets tricky. Any other questions? Any questions online?
Online, you should say.
Thank you.
Okay, let's give Daniel a hand. I just want to look at your it's not No, sorry. But it does, okay, so here it becomes more, a weaker sink, right? A weaker sink.
A weaker source and a weaker sink.
Yes. See, but also. But don't you also kind of like slow down the surface water flow system is continuous? So I guess what I'm wondering is.
It's like cuando lo tiene.
It's the opposite, you slow down the reactivity. But you also slow down the flow coming from upstream. And so maybe it's net neutral, like it's not clear what direction.
What direction is?
And I'm guessing it's not a small effect, but I asked because I feel like if I just have this conversation, come these thing out, because we're working on a thing related to log jams. And we were talking about how like when we model hydrologic exchange, we very rarely do it from the perspective of efficiency relative to what's coming downstream. We have to do it from the perspective of efficiency of what enters the downstream. But thinking about it from the efficiency of what's coming from downstream in some ways is more important from a water quality perspective.
Yes, yeah, of course.
And so, I mean, I doubt it would change the story too much, but I wish more people in our community would start to like do the extra step. So what you've done here, but then take it one step further and say like, okay, well, if the sink is weaker, but you're also slowing down surface water flow a little bit due to this morphologic roughness, is it like a net no change?
I would have to check.
Because this change is probably what, tens of percent?
Yes, yeah, it's not, it's
From
not.
here to here.
Yeah, from here.
Is there a lot of effect of the groundwater night liquefaction in the groundwater on the concentration of the river?
That's what I'm getting at, is if you, ultimately, what is that effect? Because if you slow down the flow of stream water by making your stream have to go around a whole lot more bends, you have more time for reaction, so maybe if the sink behavior is not as strong. But I don't know if it's like a few percent, the surface water resistance versus tens of percent changes in the sink behavior, I don't know.
I would say that I don't think it will not have a lot of effect the nitrate concentration. I would say it's always very large resource.
But if you do it over many tens of kilometers.
Yeah, of course.
That's what happens.
Yes, that is the other part. We hear all this is dimensionless in a way, and that's why we wanted to not think about scale. Our idea here was that if we apply the systems of the different scales, that this situation might hold in some of these areas. But yeah, I'm not sure. I have to check.
So we're not going to